So let's talk next about an important concept in astronomy, the Doppler effect. So let's start off with what is the Doppler effect? And your book does not, I'm just going to go ahead and give this is a definition. Book is not giving us a great definition there. So don't be afraid to look up resources online. This book's definition of the Doppler effect and explanation isn't the best. So we're kind of starting from scratch here. And simply put, it is change in frequency and wavelength, or better yet, change in apparent frequency in a wave in relation to an observer who is moving, or the object is moving, relative to the wave source. So let's start here with the idea of apparent. So apparent means looks like. So what we mean by this is that the observer notices the change, but someone not moving relative to the wave experiences no change, or no change in wavelength or frequency. So, and a big key here, so the big key here and big idea here that I want you to remember is that we're talking about something that's moving. That's why I'm coming back with this orange here. It only works only with moving things. Only moving. Things that stand still, it does not work for. Only moving. And Doppler effect is really, really important for understanding when we get into things like the Big Bang and that kind of stuff. Doppler effect will be important for understanding how the Big Bang works. It's also used to measure the rates of, orbits of planets. It has a variety of applications. So how does the wave change? Moving towards each other, either both objects or one object relative to the other, leads to a higher apparent frequency and shorter apparent wavelength. I can spell wavelength. Who says I can't? Clearly I can't. Look at how poorly that's written. We move forward. We're doing one take here as much as we can. Moving away leads to a lower apparent frequency and longer apparent wavelength. And this is another one of those concepts that if you get the only moving thing in this pattern here, you've got Doppler. Like, that's the big key. No matter how complicated other definitions are, Wikipedia's explanation of the Doppler effect is actually really good, and I recommend it. Not true of all Wikipedia things, but I am not a universal Wikipedia hater. It's a great way to get started in a variety of disciplines. So we use this very often with light in astronomy. So quick review. Shortwave, high frequency, light is blue or violet end of the spectrum. And long wave, low frequency, light is red light. Okay, so this is why we refer to these, when we see these relative to Doppler, we call this blue shifted. We call this the blue shift. And we call this the red shift. And blue shift is moving towards, and red shift is moving away. So, I'm going to Dora the Explorer it. We're going to draw the Earth, and we're going to draw an alien spacecraft. And I know a couple of people have already been like, Dr. E, are you joshing me? Oh my gosh, Dr. E, are you from the 90s? Yes, I am. I am from the 1990s. So, with my alien spacecraft. Aliens. And these aliens, what? I grew up in the 90s. There were a lot of alien movies. Great time for science fiction. And this alien spacecraft is moving past the Earth. So this is the motion of the alien spacecraft. Is there going to be no shift, just a red shift, just a blue shift, or a mix of a red shift and blue shift relative to the observer on Earth? So somebody's out in the desert in Nevada. So what are they going to see? Is it red shift, blue shift, no shift, or both red and blue shift? If you said both red and blue shift, then you're absolutely correct. As it approaches, this would be our blue shift because it's getting closer. Shift, shifty. And this is our red shift. Do one more Dora the Explorer. This is a good opportunity to just kind of clarify things in your mind. So here's Earth. Here's Elliot. Earth is our observer. And we have a spaceship that is traveling with Earth. It's our alien spaceship. And it's maintaining the same distance from Earth. I'm going to indicate that with no change in distance. In other words, no relative motion. Remember, Earth is moving around the sun. So if there's no relative movement, it's still like imagine like you're a boat dragging a bobber behind you, for example. Okay, so if there's no relative change. Now, would you see a red shift, blue shift, no shift, or both a red shift and a blue shift? If you said no shift, you are correct. And that's it for the Doppler effect.